So it's an immense pleasure to introduce Alex Perry from University of Michigan, who is going to tell us about surfaces on cubic fourfolds via stability conditions. Alex?
Okay, so thanks a lot for the introduction and the invitation. Yeah, so I'll be talking about a construction of special surfaces on cubic fourfolds, which goes through the derived category. And this is all work in progress with Arend Bayer, Arend Bertram, and Emanuele Macri. So in this talk, I'll work over the complex numbers, and x inside of P5 will denote a smooth cubic fourfold. So I want to start, before we say anything about derived categories, first I want to just start by reminding you about a relation between cubic fourfolds and K3 surfaces. And that's easiest to see. Yeah.
Alex, I'm sorry. Are you using Jamboard?
I'm not using Jamboard.
Ah, okay.
Yeah, if you need me to go back, you can, or I might actually be able to share a link, because you want to be able to scroll backward, is that the?
Or maybe to look later. But okay, if it's a problem, don't worry. That's fine.
Actually, I think this does work. Well, let me just put in the chat a link, which I think should work to see the notes as I go. But you'll have to reload it if you want to see like the current version. You just have to reload. Okay, so yeah, so you can follow along there if you want to be able to scroll backwards. Okay, so I'm telling you about this relation between cubic fourfolds and K3 surfaces. So let me just remind you that how does the cohomology in the interesting degree look? So that decomposes into its Hodge pieces. Okay, and how do these things look? So the dimensions of these Hodge cohomology groups, it's 0 here, and then 1, 21, 1, and 0. And so you can compare this with, if we let S be a K3 surface, then you can compare it with the cohomology of that, and they look quite similar. Okay, I'm going to put a Tate twist just to make these both be Hodge structures of the same weight. So now they're both weight 4 Hodge structures, and then the Hodge numbers here look as follows. So it's 0, 1, 20, 1, and 0, and so these look quite similar. And maybe one other thing that I want to note is that the signature of this lattice here is 19.3, and the signature of the lattice up here is 21.2. So what that might suggest to you is that if you remove an appropriate rank 2 lattice in the cubic fourfold cohomology and take its orthogonal, then you might get something isomorphic to the orthogonal of a rank 1 lattice inside of the cohomology of the K3 surface. And so that's what Hassett studied. And so actually, I'm going to consider polarized K3 surfaces. And then it's natural to remove the class, which I'll call H squared, of the hyperplane inside of here, and the class of the line of the polarization on the K3 surface. And then that leads to the following definition. So here's a definition, which is due to Hassett. We'll say that X, the cubic fourfold, is special of discriminant D. If there exists a rank 2 saturated sublattice, which I'll call K. And I want this K to contain the class H squared, and I want it to be contained in the H22 part. So I want it to be contained in the group of integral 2 Hodge classes on the cubic, and I want the discriminant of this lattice to be D. So that's sort of that's what you want on a cubic fourfold, to have one of these natural rank 2 lattices. And then we can consider the following definition, which will say that this polarized K3 is associated to X if there exists an isomorphism between the orthogonals. So I take the orthogonal decay inside of the cohomology of the cubic, and I want that to be isomorphic to the primitive cohomology of the K3 surface. And again, there's this Tate twist. So in other words, this is just the orthogonal to L inside of here. Okay, so this is a natural notion to consider. It's cubic fourfolds which cohomologically look like K3 surfaces. And Hassett studied this notion, and what he showed is the following. So let me call C sub D the locus of cubic fourfolds which are special of discriminant D. So this is inside of curly C, by which I'll denote the moduli space of all X. So that's a 20-dimensional moduli space of cubic fourfolds. And the theorem that Hassett proved is the following. So first of all, he gave a condition for when this locus is non-empty. And the condition is that the discriminant is bigger than or equal to 8, and it should be congruent to 0 or 2 mod 6. And moreover, he showed that in this case, this locus CD inside of C is an irreducible divisor. Okay, so we have a bunch of divisors in this 20-dimensional space where there is some extra cohomology class, so where there is this rank 2 lattice. And then the second thing that Hassett showed is that X has an associated K3 surface if and only if the following condition holds. So if and only if X is in CD, where D is what I'll call admissible. So admissible by definition is the following. So it's some number theoretic condition. So i.e. D is not divisible by 4, 9, or odd primes P, which are congruent to 2 mod 3. So the precise condition that I'm writing down here isn't so important, but the point is that there's an exact characterization of those D for which there is an associated K3, and there are infinitely many of those D, and they're just determined by this congruence condition. Okay, so that's a summary of the results that Hassett proved. Oops, I forgot to add extra pages. Let me add a bunch of them now. Any questions about that while I add these pages? Okay. If not, let me now say something about the conjectural relation to rationality. So here's the conjecture. So I'm going to attribute this conjecture to Sasha Kuznetsov. This isn't exactly the way he formulated it, but it turns out to be equivalent. And the conjecture is that X is rational. This cubic fourfold is rational if and only if X has an associated K3 surface. And according to this theorem, which I just explained, that's of course also equivalent to X being inside of CD, where D is admissible. Okay, so there's this conjecture. Later, I'll maybe say something about some motivation for it. Roughly speaking, it's motivated just by thinking how Hodge structures behave under blowups and blowdowns. But this conjecture is, like, I would say, quite hard. So for instance, if we knew the forward direction, if we knew that X is rational implies that X has an associated K3, that would imply a very general cubic fourfold is irrational. So earlier today, I think you heard some exciting recent work with progress in that direction. Today, what I'm going to talk about is something which is related to the opposite implication, which is also quite interesting. So the implication that if you have an associated K3, then you're rational. And so that's also a quite hard problem, I think. And let me just summarize now what is known about that problem. So when is this implication known? So it's only in a very small number of cases, actually. So it's basically the first four admissible values of D. So if D is 14, 26, 38, or 42, this is known. And for D equals 14, this is, I'll just say, a classical result. I'm not exactly sure who to attribute it to. Beauville and Donaghy certainly observed it, but I think it was known early, maybe by Fano. And these remaining three cases are much more recent. So that's work of Russo and Stagliano. And that's just in the last sort of several years, these cases have been done. And so I just want to make one remark about these cases which are known. So these known cases all depend on the existence of a special surface contained inside X. And so, right, by definition, a cubic fourfold is special if it has a surface contained in it which is not homologous to the class of H squared. But these proofs of rationality rely on a much more precise description of a surface contained in X. So let me just tell you like what those surfaces are for D equals 14 and 26. I won't tell you the rationality construction, that relies on some more intricate geometry. But for instance, if X is in C14, let's say a generic element in C14, then there exists a quartic scroll, sigma, inside of X. So a copy of P1 times P1 embedded in P5 via O of 1, 2. So there's a special quartic surface inside of X. And another example, if X is inside of C38, again, let's say generic, then there exists something called a Kogel surface, sigma, inside of X. So this is a degree 10 surface. And explicitly, maybe I can just write it down. Sigma is equal to the blowup of P2 in 10 points embedded inside of P5 by the following linear system. So you take 10 times the line minus 3 times the sum of the exceptional divisors. And that gives you an embedding into P5. And so part of the proof, for instance, of this rationality for C38 of Russo and Stagliano, part of that relies on the observation that a generic X in here contains one of these surfaces. And then again, there's some intricate geometry you have to do once you have the surface. And maybe towards the end of the talk, I'll say something about that.
Alex, these 10 points on P2 should be generic or in a special position?
Let's say generic. I think, yeah, I think you can get generic points for a generic X in C38. I think that's true. It won't be so important for this talk, though. Okay, cool. So that sort of motivates the question of whether or not, more generally for a cubic fourfold, which we expect to be rational, so one inside of CD with D admissible, can we construct some kind of special surface, some canonical surface on X, whose geometry we might use to prove rationality? So that's sort of the motivation for this talk. And so now I can state the main theorem. So here's the main theorem for today. And again, this is work with Bayer, Bertram, and Macri. So what it says is the following. I'm going to look at a special kind of D. So I'll look at D equals 6a squared plus 6a plus 2, where a is greater than or equal to 1. Then the statement is that if X is inside of this CD, then there exists a surface sigma contained in X with following degree in self-intersection, such that the degree of sigma is equal to d plus 2 over 4, and sigma squared is equal to d plus the degree of sigma squared divided by 3. Okay, the exact formulas aren't so important here, but the point is that we can produce some kind of canonical surface inside of a cubic fourfold, which generates this, this rank 2 lattice K. And maybe just 2 remarks. So maybe I can just say here, what are these D's? So the first values are D equals 14, 38, 74, and so on. So the remark is that for A equals 1 or 2, this recovers above examples. Okay, so you can check that the degree I wrote down really gives you 4 for D equals 14, and it gives you 10 for D equals 38. So this is some kind of general.
About the geometry of this surface, apart from degree and self-intersection?
Yeah, that's a good question. So I would say we don't know a lot in general about them. Like if they're smooth, for instance, we don't know. We know like the Hilbert polynomial of them, but that's about it at this point.
Thanks.
And maybe I'll say more about that later. So
Alex, is it correct that every such D is admissible?
Great, that was the next point I was going to make. So the first remark was that it was this, and the second remark is that D in the theorem are admissible. That might not be completely obvious from the formula I wrote down, but it will follow from my construction of the surface. I'll give sort of a geometric reason for why that's true later. Okay, and so the goal of the talk is to explain this theorem, and the construction will go through the derived category and stability conditions. And I think the proof of the theorem is maybe a little bit more interesting than the statement, because we do have some kind of precise description of these surfaces. And so you might hope to use them to try to make rationality constructions. So I'll mention something about that at the end. But yeah, first I'm going to try to tell you how to construct them.
And do you have a description of the moduli space of such surfaces?
They're parameterized by a K3 surface.
Exactly like for degree 14, right?
Yeah, and you'll see from the construction that they're parameterized by a K3. Okay, and so let me start. So we're gonna come back to this theorem, but first I need to tell you a little bit about derived categories of cubic fourfolds and stability conditions. So really the starting point for all of this is the following theorem of Sasha Kuznetsov. And what it says is that, so we can look at D of X. X is our cubic fourfold. So D denotes the bounded derived category of coherent sheaves on X. And the statement is that this has a semi-orthogonal decomposition of the following form. So there are 3 line bundles, O of 1 and O of 2, and then they're orthogonal to those. So if you don't know about semi-orthogonal decompositions, just very explicitly, this Q of X, Kuznetsov component, is by definition the full subcategory of all E, such that there are no X from O of I into E for I equals 0, 1, or 2. Okay, so first of all, there is a semi-orthogonal decomposition like this. And the statement of this theorem is that this category, Q of X, is a K3 category. So, i.e., in other words, Serre duality in this category behaves just like Serre duality on a K3 surface. So there's a canonical isomorphism between these X groups whenever E and F are objects in this category. Okay, so that's this category Q of X. You can think of it as it's kind of like a non-commutative K3 surface. Categorically, it behaves like the derived category of a K3. And in fact, one of the big motivations for studying this category is the conjecture that Sasha made, which is like a derived version of this conjecture that I stated up here. So this derived version of that conjecture is the following. So it says that X is rational if only if this category Q of X is equivalent to D of S, where S is a K3 surface. Okay, and so this is actually the original conjecture that Sasha made. And for instance, he showed that for the cubic fourfolds, which were known to be rational at the time the conjecture was made, he showed that this this implication holds. And more recently, it's been proven that this condition of having a derived equivalence like this is equivalent to the notion of having an associated K3 in the sense that I mentioned earlier. So this was proved by Addington and Thomas. The statement that I'll write here is a little bit stronger than what they proved, and it's a consequence of work with the following people. So I just write initials: Bayer, Lahose, Macri, Neuer, myself, and Stellari. And the statement is that there is an equivalence like this if and only if X has an associated K3. Again, in the sense that I described above, in terms of Hodge theory. Yeah, so more precisely, Addington and Thomas proved this for a generic X contained inside an admissible Hassett divisor. And in this paper with those other authors, we proved that actually it holds for an arbitrary X in such a Hassett divisor, so not just a generic one. And maybe I'll say a little bit about that theorem later. It'll kind of come up when we use stability conditions. And in fact, in the proof in this paper with these authors, our proof relies on some arguments using stability conditions, and that's what I want to review now. So are there any questions about this part before I talk about stability conditions?
So did you also prove the direction from right to left?
From right, from right to left. So if X has an associated, that I would say this is the hard direction. From here to here is the hard direction. The other direction from left to right was done by Addington and Thomas. So yeah. So maybe I should have said that. Yeah. So Addington and Thomas proved this direction, and they proved the backwards direction generically. And then as one result that we proved in this paper is that this direction holds always. Is that okay?
And do you construct the equivalence explicitly?
In some sense. That'll come up later, actually. I'll sort of mention it.
Okay.
Yeah. So now so like I said, this is going to rely on stability conditions. On this category Q of X. And so I'm just going to give you a summary of the sort of known results about this that we'll need. So this won't be, I won't tell you all the details. I'm just going to summarize here. So the starting point is a paper of Bayer, Lahose, Macri, and Stellari, which shows that there do exist stability conditions on this category. So I'll write it like this: the space of stability conditions is non-empty. So in case you're not familiar with stability conditions, a stability condition very roughly is the data that you need to form a well-behaved moduli space of objects in a triangulated category. And in general, it's hard to construct these things, but this first ingredient is that indeed stability conditions do exist. And I'm going to denote by this stability, the set of all stability conditions has a natural complex manifold structure. That's what Bertram showed. And I'm going to denote by stab dagger of Q of X, the connected component of this manifold, which contains the stability conditions that were constructed in this paper. So anyway, the upshot is that given this category Q of X, there's a whole connected complex manifolds worth of stability conditions. So then the second point that we'll need was part of this paper that I mentioned above. And it has to do with a description of the moduli spaces for these Bertram stability conditions. So I'm going to fix V inside of the numerical K-theory of this category to be a primitive vector. So just to remind you, by definition, this is K naught, the growth and deque group of this category modded out by the kernel of the Euler pairing, where this Euler pairing is the usual thing. It's by definition, chi of EF is the alternating sum of the dimensions of the X groups. Okay, so you mod out by the kernel of this pairing and you get something called the numerical growth and deque group. And the statement is that for a primitive vector in there and for sigma, a generic one of these stability conditions, we have the following. So we can consider what I'll denote M sigma V. So this is the moduli space of objects. Moduli space of sigma stable objects in this category Q of X, whose class, so if you have an object in this category, it has a class in the numerical K-theory, and I want to look at those stable objects of class V. And the statement is that, the statement that we proved is that for a V in a generic sigma, this space is a smooth, projective, hyperkähler variety of dimension minus chi of VV plus 2. Okay, so so the way you can think about this theorem is that it's sort of an exact analog of the classical statements for moduli spaces of sheaves on a K3 surface. So in this way, you can think this is another way in which this category behaves a lot like a K3 surface. Its moduli spaces of objects are nice hyperkähler varieties. And the remark that I want to make is that there are indeed many choices of V. So this does give you sort of many moduli spaces. And one way to see that is that there's always a canonical rank 2 lattice contained inside of this numerical K-theory. And this rank 2 lattice can be described as follows. So our category Q of X is embedded inside of D of X. And I'll denote by per the left adjoint to that inclusion. And so this A2 lattice, by definition, so A2 is equal to the image of all of the classes on the ambient P5 projected into the K-theory of the Kuznetsov component. So in other words, you can look at classes on P5, you can restrict them to X, and then you can use this functor to project them into the K-theory of this category. And the A2 lattice is the image of all of those sort of tautological classes. And so you see there are always many choices of this V in part 2 above. So for instance, just to give you an example, so I'll call lambda 1 and lambda 2 the generators for this rank 2 lattice. So for example, there's a really nice hyperkähler variety. The most classical one associated to a cubic fourfold is what's called the Fano variety of lines. So that parameterizes all lines P1 contained in X. This is a hyperkähler fourfold introduced by Beauville and Donaghy. And the statement is that this is actually can be realized as one of these moduli spaces in Q of X. It's isomorphic to a moduli space with vector lambda 1. And here, let me just say, so sigma is for suitable, let me say it like this. This holds for suitable sigma naught in stab dagger.
Alex,
Yeah.
there seems to be some problem with signs. So either you should put plus chi in the formula for the dimension, or you should invert the sign for A2. Notice.
Oh, sorry. Yeah, you're right. Yeah. Sorry, usually in the literature, people will use the opposite sign on this thing, but you're right. I should have put a minus here. Thanks. And so then indeed, so then this lambda 1 squared will give me, I want this thing to, yeah. So this thing will have dimension 4 because this will square. I want this to square to -2, then minus it will be 2. So +2 is 4. Thanks. Okay, so these moduli spaces recover this most classical example. And the other, so far I've told you 2 ingredients. There are stability conditions, their moduli spaces are nice. And then one other main ingredient that we'll need is a result of Lee, Pertuzzi, and Zhao, which says the following. So let's consider this vector. I'll call it V naught from now on, which is lambda 2 minus lambda 1. Then the statement is that X embeds into the moduli space for this vector. And the embedding is the following. You take a point little x on X, and you take the structure sheaf of that point and you consider its projection into the category Q of X. So the first statement is that this vector V naught that I wrote is indeed the class of a projection. And then what they prove is that this actually gives you a well-defined map. So these objects are indeed stable, and moreover, it's a closed embedding. So this is a closed embedding. And maybe I should note that this moduli space here, again, if you just use the formula for the dimension above, this moduli space is a hyperkähler eightfold. And in fact, these 3 authors, they prove something more precise. They prove that this moduli space recovers a hyperkähler variety that was classically constructed by Len, Sorger, and von Straten. So, but all we'll need in this talk is that this guy embeds into here, and this is a hyperkähler eightfold. Okay, cool. How are we doing on time? Oh, we're doing pretty good. Okay, are there any questions so far about what I've said? Okay, great. So now with these ingredients, I start telling you about the proof of the main theorem. So remember, we're trying to construct these surfaces on our cubic fourfold. And so what's the idea? Oops. So proof of the main theorem. So here's the idea. Let's suppose that we were in a really nice case. Let's suppose that this moduli space M sigma naught V naught, or maybe one thing I should have mentioned before, I didn't mention it, but in this theorem above, we show that these are smooth projective hyperkähler varieties, and they're all deformation equivalent to a Hilbert scheme of points on a K3 surface. And what I want to consider now is a very nice situation where this moduli space is actually isomorphic on the nose to a Hilbert scheme, not just deformation equivalent to one. So let's suppose that M was isomorphic to a Hilbert scheme of 4 points on a K3. So in other words, so this is the Hilbert scheme. So right, by definition, this parameterizes 0-dimensional subschemes of length 4. So let's suppose it's isomorphic to a Hilbert scheme for a K3 surface S. And then what we'll consider is for any point P in our surface, we'll consider the following 2 varieties. So the first one, I'll call it B sub P. Let me give myself a little bit more room. So B sub P is by definition the locus in the Hilbert scheme parameterizing Z such that P is contained inside of Z. Okay, so this thing inside of S4 has codimension 2, right? Just because to contain a fixed point is a codimension 2 condition. And sigma p, I'll define to be x intersected with BP inside of x. And this sigma p will be the surface that we're after. And, you know, at least for generic p, this will give you a surface indeed inside of x. And so the proof of the main theorem, the idea is that we want to find, so want to determine when that isomorphism holds. And if we have conditions when that holds, then using this construction, we can get surfaces on our cubic fourfold. So that's, I'll explain to you now how to determine when this holds. Okay, but that's the basic strategy. So the first step is a precise characterization of when this moduli space here is birational to a Hilbert scheme. So not isomorphic, but birational. So here's the statement. This is birational to the Hilbert scheme if and only if the following lattice theoretic condition holds. So if and only if there exists a class W in the numerical K theory with the following properties. So the first is that chi of W with itself is 0. And the second is that V naught pairs with W to be 1. So I just want to think about how, in terms of time, it's 4:40. So yeah, maybe I'll say just a little bit about the proof of this. So here's the idea of the proof. And let me just focus on the upward implication, which is actually the only one that we really need to construct the surfaces in this talk. So the idea is that this condition here, let me call it star. This condition star implies, and this is part of the work that I mentioned before. So it implies that this space is a K3 surface. So that part is a special case of item 2 that I mentioned above, right? So W, chi of W with itself is 0. So the dimension of that moduli space would be 2. So this is it's a hyperkähler variety of dimension 2. So indeed, it's a K3 surface. And moreover, what we showed in this work is that there's an equivalence between Q of X and ds. And the equivalence is just given by the universal object on this moduli space. So that's an object on X times the moduli space. And if you use that for a Fourier-Mukai transform, you'll get an equivalence between Q and d of S. Okay, so this condition star implies that we have an equivalence like this. And then you can look at what this does on numerical K theory. So it'll induce an isomorphism between the numerical K theory groups. And basically by construction, the class of W goes to the class of a point on the K3 surface. And where does this class V naught go? Well, our condition here, this condition, what it says is that when you translate it to the K3 surface, this is saying that V naught is a class of rank 1. And up to twisting at least by a line bundle on the K3 surface, that implies that V naught maps to the class of the ideal sheaf of a length 4 subscheme inside of S. And so now we're in pretty good shape. So let me just write it like that, like as follows. So this implies that the statement we want, it implies that it's birational to a Hilbert scheme. And the idea is just that on the left side, we're taking moduli space of objects with respect to this vector. And on the right side, we should take a moduli space, because this isomorphism takes V naught to the ideal sheaf of a length 4 subscheme, we should take moduli of objects with that class on the right side, which is indeed a Hilbert scheme of a K3. So technically to see this implication, you have to use work of Verbitsky and Markman. on the hyperkähler-Torelli theorem. But basically, the point is that because of this isomorphism taking V naught to this class, there will be an isomorphism between what's called the Mukai-Hodge structure of S and Mukai-Hodge structure of Q of X, and that isomorphism will take this class to this class. And the work of Verbitsky and Markman imply that these two varieties are then birational. So that's sort of just a sketch of what goes into a proof here. But that's the first ingredient in the proof. So we have this precise condition for when there's a birational isomorphism between these two spaces. Okay, so what's the second step in the proof? The second step is basically just a computation. So I'll just write the statement. It's sort of a lattice theoretic computation that this condition star from above, the existence of W, which pairs to 0 with itself and to 1 with V naught, this turns out to be equivalent exactly to that condition in our main theorem. So it's equivalent to X being in CD with D equal to 6A squared plus 6A plus 2, where A is bigger than or equal to 1. So this gives some kind of explanation for where that specific form of D in our theorem was coming from. So again, that's just a computation. And now what's the third step? The third step is let's consider an X in CD, where again, D is 6A squared plus 6A plus 2. And I'm going to consider A bigger than 1. You can kind of ignore A equals 1. And let's assume that this is very general. Then what we show is that this implies that the Hilbert scheme of points on our K3 has no birational smooth K-trivial models. So in other words, what we prove is that whenever you have a smooth variety with smooth projective variety with trivial canonical bundle, which is birational to S4, then in fact it's isomorphic. And so in particular, by step 1, right, that implies that our moduli space is indeed isomorphic to this Hilbert scheme. And so maybe I won't really say much about the proof of this, but I'll just say it uses work of Bayer and Macri, I think from 2012 approximately. So Bayer and Macri have a really nice result, which it gives you basically complete control over all birational models of a Hilbert scheme of points on a K3, or more generally of moduli sheaves on a K3. And what it does is it reduces proving a statement like this to showing that certain Pell equations have no solutions. So once you use this as input, it sort of boils down to some computation where you show certain equations have no solution using this form of D. So that's like the basic idea of the proof. So hopefully that explains to you where this condition is coming from. And then again, our surfaces are just constructed as intersections of X with this locus inside of the Hilbert scheme. Are there any questions about the sketch of this proof?
Yeah, suppose you want to cover other Ds, then you would have to look at Hilb n for other n's rather than 4. You picked the simplest one, presumably, yeah?
Well, there are different ways. There are various ways you could try to do it. You're asking for other discriminants, right?
Yeah.
Yeah. So actually, let me make a remark about that. There's actually one thing that you can do just using Hilb 4 still, and actually, it already should cover almost all of the D. So let me make a remark about that. So more generally, you can try replacing this BP, so this codimension 2 locus in the Hilbert scheme from above. So we can try replacing this BP inside of here with, or maybe, sorry, I might have said something wrong. I'm going to say basically exactly what you were suggesting. And what we'll replace this with is certain Brill-Noether loci. So instead, what we're going to consider is the following. we'll consider again a class in this numerical K theory. But this time I won't require that that class has square 0, just any class inside of there. And I'll require that it pairs with V to be 1, okay? And then instead of fixing a point on the K3 surface, now I'm going to fix a point F in this moduli space, right? So in the case where W squares to 0, I would just be fixing a point on the K3. So let's fix this data. Then instead of BP, we can consider the following locus, which I'll call the Brill-Noether locus for F. I'll consider the locus of E inside of our moduli space, where the HOMs between E and F have dimension greater than or equal to 2. So the way you should think about this is that this condition is telling us that generically we should expect that there's just a single HOM between E and F. And then we can consider this locus of all E where the HOM jumps. And I'm calling that this Brill-Noether locus. And the reason that this is a reasonable thing to consider, this has expected codimension 2. So the one thing I should emphasize, that's just the expected codimension. And if you could prove that that had expected codimension 2, then you should be able to do exactly what we did above. You just intersect it with the cubic. But currently, we don't have a general proof that this has the correct codimension. And maybe I can just say, so this would indeed cover many more D. So I think this condition here, the existence of a W that pairs to 1 with V naught, I think that's equivalent to D congruent to 2 mod 6. So it would cover like half of the discriminants. Does that answer the?
But this time, these surfaces will not be parameterized by a K3 surface, right?
That's true. They'll be prep. Yeah.
Mm-hmm. And another thing, are the corresponding values of D all admissible?
Not in this case. So I was saying in words, I think that you get all D congruent to 2 mod 6 this way. Yeah, but indeed, I mean, we would sort of expect, right, that for any Hassett divisor, there should be a special surface. And what I'm saying is that if you, I mean, we haven't done this, but I think we expect that this will work. If you could make this construction work, you would already get half of the Hassett divisors, not just admissible ones.
And what do you get for degree 8?
What do you get for degree 8? Oh, well, you just get a plane. Yeah, you get a plane in that case.
Exactly.
Okay. Yeah. Okay, cool. So yeah, so this is, so far what I've said is I've basically sketched for you the proof of that main theorem. And I think I have 10 minutes left. So in the remaining time, I just want to say a little bit about how you might try to use this to say something about rationality. So maybe I should say right off the bat, we don't know how to prove rationality. We don't know how to prove rationality of cubics X contained in CD, where D is of this form here. But the hope would be that maybe you could use these surfaces to prove, well, the best hope would be you could prove it in general, but maybe you could prove some new cases. So this is something that we're thinking about, and maybe I can just say a little bit about that now. So what about rationality? So let's work in the situation of the theorem, so of the proof that I just gave you. So I'm going to fix P and S, BP inside of the Hilbert scheme, and sigma P inside of X as above. Okay, and so if you wanted to make some rationality construction using this surface, it would be natural to ask, like, what rational map gets resolved by blowing up this surface sigma P inside of X? That's a natural thing you could ask. And one way to think about that is as follows. So we have this Hilbert scheme, S4, and you can consider, instead of the blowup of X in sigma P, you could consider the blowup in BP of S4. And what rational map gets resolved by this blowup? Well, it's the following very natural map. There's a map from S4 to S5, which takes a length 4 subscheme, and it just adds on this point P. Okay, and the locus that you need to blow up to make that rational map regular is exactly the locus of Z, which contain P. Okay, so you get a diagram like this. And now we can sort of just restrict this to X, right? So our X is sitting inside, it's embedded inside of S4. And so we can consider this blowup in sigma P of X, which is sitting inside of the blowup here. And if you follow this map through, what we'll get is an embedding of our blowup of X into the Hilbert scheme of 5 points on this K3 surface. And the idea, so, and again, this is very much like in progress still, with Bayer, Bertram, and Macri, is that we can try to run the MMP on this Hilbert scheme of 5 points, and we can follow what happens. To the blowup of X in this surface. And so let me just give you like one example, an example that was already known, so by Russo and Stagliano. So let's consider the case example where A is equal to 2, and then in that case, D is equal to 38. So it turns out and again, to run MMP on Hilbert schemes, it's sort of just ends up being a computation using these results of Bayer and Macri that I mentioned earlier from their 2012 paper. And so if you use those results for S5, what you end up finding is the following. So if you look at S5, there's a diagram as follows. So there's a contraction onto something I'll call M1 bar. And then there's another contraction of that onto something I'll call M2 bar. And these spaces on top are all birational to each other. And I'll tell you what they are. So this first diagram here, this is a flop at a P3 bundle over the Fano variety of lines inside of X. So in that first triangle is contracting some P3 bundle over the Fano variety of X, and we get a flop of that thing. And on the right-hand side, what you end up getting is a flop at a P2 bundle over S times F of X. So S is our K3 and F is again the Fano variety of lines. Okay, so, and it turns out that that's not the whole MMP for this Hilbert scheme, but we'll only need those first two steps to see rationality of the cubic. So this is what we get for the Hilbert scheme. And what happens when we restrict to our fourfold? So what turns out happens is the following. So we have X, we have the blowup, and that diagram restricts to a diagram as follows. Okay, so this first thing here, maybe I can use color actually. So this thing here is a flop at the 3 secant lines to sigma contained in X. So it turns out that if you look at all of the lines contained in the cubic fourfold, which are secant to this surface sigma, that sweeps out a surface inside of X. And this first map above, when you restrict it to the blow-up of X, it induces a flop to this variety, which I'm calling X1. And it's flopping exactly that locus of 3 secant lines. And then what happens in the second step is that this X2, the base, let me make it black again. This base, it turns out, is actually isomorphic to P4. And this map here is a divisorial contraction at the 5 secant conics to sigma. So you look at the locus of conics contained in this X, which are 5 secant to our surface sigma, and this map is contracting those. And it turns out the base is P4. And so this is in particular giving us an explicit birational isomorphism of X with P4. But the thing which I want to remark and emphasize, so note, oops.
And what happens to M2? So you had M2 over M2 bar. Why don't you have X2 over X2 bar?
You could keep going, but for the rationality construction, you don't need that. That's a good question. I'd have to maybe let me not say right now what happens when you go to M2 with X. But for the rationality construction, at least, you don't need that. But the thing that I did want to emphasize is that, oops, at the moment, the above uses, so we use as input Russo and Stagliano's results. So it does not give a new rationality proof. So what I'm saying is that at the moment, to prove these things, like for instance, to see that the base is P4 and to see exactly what you're flopping, at least at the moment, to see that we're using a comparison with Russo and Stagliano's work. The hope would be to have a proof which is independent of that, but we don't have that yet. But at least what I think I can say is that this gives a very natural interpretation of the rationality construction. It sort of just pops out from the construction of our surface. You have this surface blowing up X in the surface is naturally giving you a map into the Hilbert scheme. And if you just run the MMP on the Hilbert scheme, it induces the birational map to P4. So I think it's a nice picture, but at the moment, we can't use it to prove rationality. Okay, and I think that's all I wanted to say.
All right, let's thank Alex. Questions?
Alex, in case you will replace the Hilbert S4, this Hilbert scheme by the moduli space M sigma 0 of W, what is going to be the first step of your rationality construction?
Oh, you're saying in these other cases, can you make a similar construction, right?
Yes.
Yeah, you can try to do something similar. Like I think in that case, when you take the blow up, it'll be resolved by like a space of maps. Instead, you'll be looking at, maybe you fix this this F, and you'll be looking at something like a space which has of E's which are equipped with a map from F, and then you can take the cone of that map, and you'll get a map to another moduli space, and that's sort of a natural generalization of this picture here. So this S.
Is it going to be the moduli space something like V0 minus W? Or?
Exactly, yeah, exactly.
So S5 will be replaced by this moduli space.
Exactly. And we are considering those kind of cases too, and I think it can be useful in those examples as well.
Other questions? All right, let's thank Alex again. So, and we'll proceed tomorrow at 9 a.m. Eastern Standard Time. Thank you.